Hello, everyone, and welcome to our webinar. If you've ever struggled with wavefront distortion in your high-power laser systems, you know it can be a major roadblock. But what if you could correct those aberrations with incredible precision, even at full laser power? That's exactly what we'll be exploring today in our webinar, Hands-on Large Dynamic Range Mechanical Deformable Mirror for Aberration Correction at Full Laser Power. I am Omar Kobaiter, your host, and I can't wait to show you how this is game-changing. So following will be our agenda. We'll start by introducing the company, presenting the product Elawstar. We'll have a live demo, and we can answer all your questions in the Q&A session at the end of the webinar. So for those who may be unfamiliar, Imagine Optic has been a pioneer in wavefront sensing, optical metrology, and adaptive optics since 1996. We are a privately owned company dedicated to developing and manufacturing high-performance, versatile solutions for a wide range applications with a strong global presence and commitment to continuous innovation. So as you can see, we're more than 60 employees and we have more than 30 patents. In 2003, Imagine Eyes was created dedicated to ophthalmology, and in 2024, Shocklight, a sister company, was created dedicated to laser shock pinning. We have sold more than 2,000 sensors and more than 100 Elawstar systems. Following is an example of our base of clients for optical metrology and for optical correction. And I will explain to you what we offer. So we have on the left side the analysis products, wavefront sensors and optical metrology systems, and on the right side the adaptive optics solutions and the deformable mirrors that we will delve in one of them in today's presentation. I leave the word to Xavier and Alok.
Thank you, Omar, for introduction, and thanks to everybody again for joining us. Uh, to have a look with us. Our adaptive optic system, which is very specifically designed to meet the requirements of state-of-the-art high-power lasers, and uh, perhaps everybody perhaps everybody might be familiar that high power laser system often face the issue of wavefront distortion coming from either misaligned optical elements or mechanical constraints coming from large optical components on large optical components because of the way they are mounted, or and other factors that can also induce wavefront aberration in high power beam. They include thermal effects in laser amplifiers. Mm. Of course, many of these effects, they have been observed and reported in the past, uh, and uh, as a consequence of all these aberrations being induced in the wavefront, uh, the focused beam quality is severely degraded, which of course is not very good for applications that need maximal intensity at the focal plane in the interaction zone. So to improve the wavefront in optical systems, traditionally adaptive optic system, particularly with deformable mirrors, based on different techniques have been used. For example, MEMS, PIMORPH, piezo, and magnetic too. Of course, every system has their shortcomings and their advantages, but in the context of high power laser, it is very important to mention some of the shortcomings which are critical for such application. For example, what we need is a deformable mirror which is insensitive to electromagnetic perturbation, particularly if we want to use our system to study light matter interaction in high intensity regime. At the same time, it is also needed to have needed to have low hysteresis value, and very often the other alternatives such as piezo or bimorph or MEMS, they suffer from poor reproducibility and high value of hysteresis. And another concern for these these systems is poor temporal stability coming from creeping effect. And some of these mirrors, they also suffer from print through, because it is required to use very thin reflective membrane in some for some of these technologies. So when we started to develop this mirror based on mechanical actuators, our motivation was how can we have a system which removes or these issues I completely I to well in the ideal case, but if not completely, then at least partially. So just a moment. Okay. Okay, so to tackle the issues that I mentioned, we developed deformable mirrors based on mechanical actuators, and they indeed solve some issues. For example, they because they are not required to have supplied any current to maintain their current position. They are completely insensitive to electromagnetic perturbations, unlike many other alternatives such as MEMS, bimorph, or piezoelectric based mirrors. At the same time, as we have the possibility of using powerful actuators, we can utilize very thick reflective surfaces, which reduces the print through effect drastically and thus improves the optical quality. Um, at the same time, these mirrors, they turned out to have very good temporal stability, no creeping effect as what is seen in bimorph mirror. Of course, we did manage to solve some issue with the initial version of the deformable mirror based on mechanical actuator, but not all the issues were solved. For example, the initial version, they were prone to backlash, which was affecting the reproducibility. And to have a good reproducibility, one of the alternatives was to use multiple movements when moving the actuators. What I mean to say is, with multiple movements, we can approach a certain position from the same direction. And we can use this approach to have very good reproducibility. So at the end, this allows us to have good reproducibility, but at the same time, it gives us not very ideal closed loop behavior. And also it generates intermediate, because we are relying on multiple movements, it generates multiple shapes or intermediate shapes within the closed loop, within single closed loop. And of course, in the context of high power laser, this is far from ideal, because if we generate intermediate wavefront shape, it might lead to uh, intensity distribution, where locally we can have fluence, very high fluence, which can damage many several sensitive optical elements, including laser compressors. So the challenge we undertook is to try to have a deformable mirror which simultaneously is able to give very good reproducibility without generating any intermediate wavefront shape within the correction loop. So as I mentioned, our deformable mirrors are based on patented mechanical actuator technology, where we have two parts. We have linear motor, as you can see here. We have a linear motor, and we have the floating head. And these floating heads, they are at the back of a continuous reflective surface, and by pushing and pulling the linear motors, uh, we can locally deform the topology, or let's say surface topology of the reflective surface, and this allows us to modulate or to modify the wavefront of the incoming light. So, of course, as I mentioned, we are trying to have a deformable mirror where we want to have um, very good reproducibility, as well as while doing single movement, thus no intermediate shapes. And to have this, what is needed is high linearity. So here we can see experimentally measured linearity of a given actuator, and from the linear fit, we can see that the linearity is over 99.9%. And on the bottom left, we have the hysteresis curve measured over the whole range of the actuator. And as you can see, it is pretty low. Sometimes it is even difficult to measure. So at the same time, as I mentioned, that our objective is also not to do multiple movements, because, well, there are two outcomes if we do multiple movements. We generate intermediate shape within the adaptive optic correction loop. The second one is, because we are spending time in doing two shapes, it reduces the closed loop correction frequency. Okay, so here what we are doing is just single movement, and this also allows us to have uh, closed loop correction frequency more than over 10 hertz, close to 12 hertz. As you can see here, we are able to induce 3 micron peak to valley of curvature at a frequency over 10 hertz, thanks to the single movement motion approach. So of course, our new system is able to, let's say, deliver reproducibility, as well as without generating any intermediate shape. At the same time, if we want a system, an adaptive optic system, to be able to work at full power of the laser, we need to have some security features. So having this in mind, we have tried to integrate some safety features in our system, in our adaptive optic system as well. So here we have our every electronic control box of our deformable mirror has possibility of either sending in a trigger TTL trigger signal, or having a TTL signal out of the electronic control box. And this allows us to synchronize our movement of our actuators with the laser system, and as well as it provides us opportunity to manage uh, the duration during which our actuators in the deformable mirror are moving. For example, we can consider a situation, let's say a laser of 10 hertz, and we can use, let's say, a TTL signal trigger in. So if we have 10 hertz, the time duration between two successive pulses is 100 milliseconds. And what we can with this approach, what we can ensure is that there is no change in the shape of the deformable mirror while my light is on the laser pulse is on the reflective surface. So here we have, let's say, a certain deformation. Our wavefront sensor measures and calculates what sort of deformation has to be applied to the surface of the deformable mirror to correct for certain aberrations. So once we have the TTL signal coming in, the corrections are computed, and then these corrections are applied only after the successive pulse. Okay, and similarly, another layer of safety we can have is to have a TTL out trigger out signal, where one can monitor um, when our actuators in our deformable mirror are in motion. So combining these all these factors that include high linearity, very low hysteresis, and possibility of having very good correction quality while doing a single movement. And when we couple this with the security features, uh, it opens the possibility of having closed loop correction for for high power lasers at full power, in fact. And indeed, this has been demonstrated with our deformable mirror for a petawatt class laser at LI Alps. So of course, we are able to, most of the parameters related to our deformable mirrors are customizable. For example, we can have deformable mirror for different beam geometries, beam diameter ranging from 20 millimeters to 600 millimeter. We can also customize the angle of incidences, the number of actuators depending on the kind of correction capability one requires, uh, as well as the coating, the reflective coating. We are able to have very hard coating as well, like IBS and IAT, and we can also have mirrors that are able to work under low pressure at high vacuum, I mean. And my colleague Xavier, he's going to show you hands-on operation of a deformable mirror, our new generation deformable mirror, which is a vacuum compatible one.
Yes, but before that,
Yes, but before that, thanks for reminding me. Okay, of course. So as I mentioned, we can customize several parameters of our deformable mirror. And to show you, let's say, a selected case of extreme optimization, here we designed a deformable mirror, uh, which which is let's say which is adapted in such a way that it can provide desired correction quality for wide range of beam diameters. What I mean is, starting from, it can provide very good active flat quality for 60 millimeter beam up to 160 millimeter beam. And of course, we achieve this by very specific spatial distribution of the actuation points
yeah, the number of
and the number of actuators.
Okay, so let's say that it's time for the demo. So thank you, Alok. And first of all, I will present you the setup. So the setup is based for sure on our new deformable mirror. And this deformable mirror is what we call a 150 millimeters diameter deformable mirror. So that is to say that the membrane itself is 150 millimeter diameter. The active part of the diameter, beam diameter correction is 75 millimeter here. And this deformable mirror present 37 actuators. On this mirror, you can see that there is a dielectric coating dedicated for 800 nanometers. And in front of this deformable mirror that is mounted on a special gimbal mount here, we have placed our Airflex LA 150. And this is basically a wavefront sensor with the light source at 785 nanometers. And thanks to the LA, the Airflex LA, the light is collimated on 115 millimeter diameter. And so the light is reflected by the mirror itself, and the light is then analyzed by our wavefront sensor ASO4BB. So let's have a look now on the software part. So here I'm going to use our WaveTune software, and basically WaveTune software is a software that is dedicated to a closed loop, open loop control of deformable mirror. So here we do have a departure point that is not perfect, of course. And as you can see here, we do have an aberration that is more than 2.5 micron PV, 0.6 micron RMS. And if you are looking at the focal spot, we can see that the focal spot is not beautiful at all. And thanks to this focus spot, we are able to calculate a Strehl ratio that is around 8%. So before this webinar, I have made what we call the interaction matrix. That is to say that I've recorded or the influence function for each actuator. And here for this webinar, the target for the closed loop will be to be able to have the best correction, that is to say the best focal focus spot. For the beginning, I will do a closed loop with this parameter. So we will work with 30 degrees of freedom, with 37 actuators. We theoretically have 37 degrees of freedom, but in order to be in a very robust configuration, I decide to just select 30 of them. And we will work with a low gain at the beginning, so let's say 0.2 gain, and we will work in a continuous configuration for the closed loop. So now the waveform sensor is working, but the closed loop is not, it's off. So you can see the aberrations, and now I will close the loop, and you will see the beam that is better and better and better. The focal spot is becoming quite perfect, close to the best focus spot we can get. Here you can see that the aberration, the correction is better than 20 nanometers RMS, and for sure with this optical quality, the Strehl ratio at the end is close to 1, more than 0.85. So just to remind you, everything here is done with in a single movement mode, and for sure in this configuration with single movement mode, our closed loop is working very well. In order to show you the perfect linearity of this mirror, I will come back to the departure point that is not very good, as we can see here. And now I will configure the closed loop with a gain of 1. That is to say, we are going to measure, and we are going to measure the aberration, and we will correct. We will ask the closed loop to correct the aberration in one iteration. And to be sure of that, I will configure the software to do only one iteration. That is to say that the waveform sensor will measure the aberration, calculate the command, send the command, and that's all. No more iteration. So the wavefront sensor is measuring, and now I will close the loop for one iteration only. As you can see, now the closed loop is off. The wavefront sensor continue to measure, but the closed loop is off. And in only one iteration, we are able to reach a perfect beam. So we are able to correct all the aberration. Now the Strehl ratio is above 0.95. The wavefront correction is less than 30 nanometer RMS, and everything was done in a single movement and only one iteration. I'm quite impressed by this mirror. But now I would like to show you the reproducibility of this deformable mirror, and it's one of the main improvements we have made in this last version of mirror. So to do that, I won't do any closed loop anymore. I will only put some shapes that I saved before the webinar. And the first shape I want to show you is an astigmatism at 0 degree with 200 nanometers RMS value amplitude. And here we are just measuring the wavefront with a wavefront sensor, but without any closed loop. And the result is, for sure, the astigmatism you can see here, but the result you can see on the point and function, that is a pure astigmatism. The other shape we can see here is the same astigmatism, but turned at 45 degrees, and I will put it directly on the mirror. And once again, everything is done in a single movement mode. So without any intermediate shape, we are going from the previous shape to the following shape in only one movement. And once again, it's a perfect astigmatism. And let's continue with comma, for example, comma at 0 degrees.
Textbook example.
Yeah.
Yeah.
A beautiful comma, and to finish, I have also a comma at 90 degrees. So I've put several shapes here, and now I will show you that we can come back to the perfect shape and the perfect correction without any iteration for the closed loop, just loading the shape that was before. And as you can see here, we can reach a Strehl ratio that is above 90.95 for the Strehl ratio.
Single movement.
Always single movement. So honestly, we are kind of proud of this achievement, because it's a real challenge to be able to have such behavior in open loop for deformable mirror based on actual mechanical argument. So